All right, so we're on to the next segment of this module, and this is where we're going to start kind of reviewing complex numbers and start talking about phasors, heavily related to what I talked about in the last slide. We're going to get there pretty shortly, so let's get right into it. So first things first, we need to talk about the complex plane and complex numbers. I'm sure you remember complex numbers. Pretty similar to our rectangular coordinate system where we have x on the x-axis and y on the y-axis, or I guess you would say x on the horizontal axis here and y on the vertical axis. However, for complex numbers, like for example, I wrote 6 plus 4i here, kind of just sticking with my example from earlier. What I would say is that my real part of the number, because a complex number basically consists of two parts. It consists of a real part and it consists of an imaginary part, okay? And we sort of have our two axes here, where on the horizontal axis we have our real axis or our real numbers, and on the vertical axis we have our imaginary axis, right? Okay, so if I'm looking at a complex number, it's broken up into two parts, where the real part is the part that does not have an I, attached to it, and the imaginary part is the part that does. And that's how we distinguish the two parts. So actually in the next slide I kind of talk about that. This is called rectangular form of the complex number. It's basically a complex number z, which in this case I could say is equal to 6 plus 4 times I. It's actually got a real part. So I could even write out the function, like you'll see this, some kind of notation like this. The real part of z is equal to 6. And then the imaginary part of z is equal to 4. It's important to note that the imaginary part of z is not 4i. Rather, the imaginary part is the part that is multiplied by the I, okay? And so what I'm looking at when I look at rectangular form is I'm basically just looking at the x coordinate, which in the complex plane happens to be the real coordinate, and the y coordinate, which in the complex plane happens to be the imaginary coordinate. That's just the way that we write numbers in rectangular form, right? And so that's kind of what I have written right here, that z is equal to x plus iy. However, I think it's very important to stop right here and kind of make the distinction. Maybe I made this mistake in some slides moving forward, but in engineering, of course, we know that I is equal to the square root of -1. That's what we learn when we learn complex numbers. However, in engineering, we do not use I because I is reserved for current, so that would get very confusing. Instead, what we use is J. Okay, so this is just my complex number review. That's kind of why I included I's in here. But what you will see in engineering in general is you would see that the imaginary part is actually denoted by a J. Okay, so we're going to have to get used to seeing that, but just note that we don't use I is equal to the square root of 1 because I is reserved for current. Instead, we use J is equal to the square root of 1, and everything stays the same. Okay, so then this would just be a J, this would be a J, and we would be on our way. Okay, and so that's what we're going to do from this point forward. Probably, if I mess it up in some future slides, I'm probably not going to change it, but just keep that in mind that I am going to, from this point forward, utilize the J for the square root of -1. Okay, but hopefully it's clear at this point that what we've done is we've shown that a complex number. I'm actually just going to get rid of those J's for now. But just note that this is the fact. The facts of electrical engineering is that we are stuck using J instead of I for complex numbers, okay? But what we've covered so far, just a real brief review of complex numbers, is that there is a real portion and an imaginary portion, and that when we plot it in the complex plane, we have a real horizontal axis, an imaginary vertical axis, and so a number can be plotted at a point on those coordinates, and we can write it just like this, 6 plus 4i, or in our terms, 6 plus 4j. There is another form called phasor form or polar form, which we talked about previously, where we can write it in terms of the magnitude, right? The magnitude being the length of the vector from the origin out to that point, again, like we talked about previously, and the phase angle, or the angle from the positive x-axis. In this case, again, since I'm using the same numbers, my magnitude is 7.2 and my phase is 33.7 degrees. And so this is a separate way to write out or to represent complex numbers. So we have the number, which we know can be written in rectangular as 6 plus j4. Or in old terms, how you learned it in school, 6 plus 4i, but I'm not going to write that. I'm going to go to j from now on. Or we can write this in phasor form by, again, we could convert to the r, which is the square root of 6 squared plus 4 squared, which gives me 7.2. And the theta, which is the tan inverse of y over x, or in this case, it's 4 over 6. Which gives me 33.7 degrees. And then I can rewrite z as r angle theta, or 7.2 angle 33.7 degrees. Okay, so these are interchangeable interchangeable forms of complex numbers. There is the rectangular form here on the left and the polar form here on the right. Okay, hopefully nothing new here, kind of just what we already covered previously about general coordinates and general vectors, but now we're doing it instead of in the x, y coordinate plane, we're doing it in the complex plane. Nothing's changed, okay? So I'm going to go ahead and stop this video right here. I think it's getting a little bit long.